We will now start a discussion on perovskite materials. This is the most important class of piezoelectric materials. The reason is that the most widely used piezoelectric materials are ceramics, and most of them have the structure of perovskite materials. So if you are going to use piezoelectric materials, there is a high probability that it will be a perovskite. We will also discuss other structures such as wurtzite and fluorite at the very end. We will also use perovskite materials to introduce two very important topics, and that is morphotropic phase boundary, which is a structural feature in the phase diagram of complex materials, and also concepts of hardening and softening. So they have all been observed first in a perovskite materials, can exist in other structures. We have already given some introduction in perovskite materials. An important feature of perovskite is this octaeder of oxygens, and much of the properties that I will explain is present actually because of this particular feature of perovskite materials. Here a list of some of the compositions that belong to perovskite materials. First, there are some ferroelectrics, such as barium titanate, which we already discussed in some detail, potassium niobate, lead titanate, lead zirconate titanate, already a solid solution between lead zirconate, PbZrO3, and PbTiO3, lead titanate. And that's the materials that most of our discussion will be oriented towards. And then we have a class of so-called relaxor materials, which by themselves are not ferroelectric, or at least not at room temperature. But when we mix them with one of these ferroelectric compositions and we get relaxor ferroelectrics, then we also can get very interesting properties. And the materials with the highest piezoelectric coefficients are actually solid solutions of this material, which is called PMN and lead titanate. And we will discuss those also. I will not talk much about relaxors themselves, but we will discuss relaxor ferroelectrics. However, the most important concepts such as morphotropic phase boundary, hardening and softening, we will explain on a PZT. Probably 90%, at least in volume, of all piezoelectric materials used today is PZT. And there are other compositions and thousands of solid solutions. As I already said, these are not only structures, there are others that we will mention toward the end. So one important feature of PZT, so PZT is a solid solution of lead titanate and lead zirconate. So if you start with the titanium and you start replacing titanium with a zirconium, you get PZT, lead zirconate titanate. Here is the phase diagram. This phase diagram is, here you have a composition. So here is 100% lead titanate. Here is 0% lead titanate, or 100%. So this would be 100% lead zirconate. Here is mole percent of lead titanate. Here is the temperature. Material is cubic. There is a complete solid solution everywhere. You get a single phase. There is a boundary which separates cubic non-ferroelectric phase from cubic phases, and this goes from about 500 degrees down to about 200 degrees. The phase diagram is divided roughly in two parts. by vertical boundary. So boundary that depends very little on temperature. It bends a little bit here at the end. On the right side, on the lead titanium rich side, material has a tetragonal structure, and on the rhomboedral side, material has a rhomboedral structure. You can ignore this division within a rhomboedral field. There are two different rhomboedal structures, but that is not important for our discussion. There is an orthorhombic anti-ferroelectric phase with less than 10% of lead titanate, and that phase as well is not important for us in the discussions that will follow. So just consider this whole thing as being rhomboedral, and this one is tetragonal, and here we have a cubic phase. Now, this vertical boundary is interesting because piezoelectric coefficients and also the electric permittivity and elastic compliance all have a peak at around 52% zirconium and 48% lead. And that is why this material is interesting, besides being able, besides being easily manufactured in form of ceramics, being relatively inexpensive. This name, morphotropic phase boundary, is the name that Goldschmidt gave to the feature in the phase diagram where you change one element in a compound with another, and by adding more and more of this second compound, by keeping all the time the solid solution, you come to a position where adding just a little bit more of second compound of replacement, you change the structure. The definition doesn't say anything about having large properties, but that is assumed today, that if you have a morphotropic phase boundary, is that you would have large properties. Goldschmidt is a person who is responsible for almost for creation of the whole field of crystal chemistry, and has been the first, he and his group were the first to synthesize most of the perovskite materials, including barium titanate, lead titanate, and so on. And the PZT, however, was first synthesized in 1950s in Japan by Shiran and others. So we are interested in why these properties are high at the morphotropic phase boundary. Why should properties increase by a factor of, if you look here for a D15, coefficient increases by a factor of 2.5, D33 also from 100 to 200, so 2 times increase is not trivial, and actually you can get even higher. In a practice, it depends how you prepare your ceramics. Interestingly enough, one end member is not ferroelectric at all, and you will notice that same thing in other materials with the morphotropic phase boundary, that one end member is not ferroelectric at all. So we don't have morphotropic phase boundaries, as far as I know, between two ferroelectric, properly ferroelectric phases, maybe NBT, which we will see later on. Yes, NBT would be the one where you also have ferroelectric phase on both sides of the phase diagram. But that's not important for us. Now, this phase diagram that I'm showing here is from I think 1971. You will find it in a book by Cook and Jeffy, Piezoelectric Ceramics, that I gave you reference. for which I gave you reference. And since then, there were improvements in this phase diagram. And the different authors actually disagree in how this phase diagram should look like. And it actually depends a little bit on how you approach it and how you interpret the results. So in this phase diagram, you have basically the same tetragonal and rhomboedral phase, but rhomboedral phase is very rich. There are other phases appearing there, and then there are also some monoclinic phases appearing between most importantly tetragonal and rhomboedral phase. And it is this monoclinic phase which is actually very interesting, and I will try to relate that monoclinic phase to this fact that the largest increase in the properties increase is actually observed in a shear piezoelectric coefficient. And then there are other researchers. This one is from by Glaser, relatively recent result in which he showed that this whole field here of a rhomboedral material can actually be considered to be monoclinic, which changes as we keep adding titanium. It actually changes monoclinicity, however you define it. And so that large range here toward the morphotropic phase boundary is actually a monoclinic phase. So there is this monoclinic phase that keeps appearing. The monoclinic phase was discovered by Nogueira and Shiran, I think at the end of 1990s, around 2000. And that was a big surprise because that monoclinic phase was not expected. Theoretically, people were using sixth-order Landau-Ginzburg-Devonshire theory, which doesn't support monoclinic phases. But if you add more terms, then you can get it. And that was theoretically also done. So one important one possible explanation why in ceramics, and people had available only ceramics for a very long time for PZT, single crystals are very difficult to make. So there was some explanation that this morphotropic phase boundary is just related to a ceramic polycrystalline nature. And what do you have to do to polycrystalline material to make it piezoelectric? Well, you have to polarize it. Now, in a PZT, you have in tetragonal phase six positions, 6 orientations of polarization vector, and you have 18 for a rhomboedral. And when you are at a morphotropic phase boundary where two phases meet, if two phases meet at the same composition, that means that energy between those two phases cannot be very different. I will discuss that next. And if they are very different, if they are not very different, that means that even with relatively weak fields, we can go from one phase to another, or that we can rotate polarization from tetragonal equilibrium directions into rhomboedral equilibrium directions. And since we have 6 in tetragonal and 8 orientations of polarization in rhomboedral, then at this position here we can easily have access to 14 different directions. Energy between them cannot be too different. And therefore, you can pole ceramic more efficiently. That is what is simple explanation of this morphotropic phase boundary for ceramics. However, theory shows, and this was done by Hone Mike Hone and Eric Ross showed that peak in properties also appear in monodomain single crystals. So this was done by thermodynamic calculations. LGD stands for Landau, Ginzburg, Devonshire. And if you look at the books by these papers by Hone, you will find reference for the Devonshire extension of Landau-Ginzburg theory. So they showed that this is also that this is an intrinsic property of the crystals, that it is not just a mere consequence of pooling of the material, although this argument with the free energies being very close of rhomboidal and tetragonal phases hold. And what you will see, and this is very important, is that the largest coefficients are transverse permittivity. Here, the authors use eta for permittivity. This is actually our kappa or epsilon, or if you work with the susceptibility, he. So that transverse permittivity and the shear piezoelectric coefficient are the ones that become largest as we approach this boundary. And it's interesting to look why this is so. So just to come back to these energy arguments that I just mentioned, if you have two phases such as tetragonal and rhomboidal in a phase diagram, and if you smoothly go from one to another, you don't create any secondary phases, there is no phase separation, you always have a solid solution. So once you come in tetragonal phase close to rhomboidal, you just add a little bit of zirconium atoms and structure changes into rhomboidal. What that means is that free energy of tetragonal phase is lower than free energy of rhomboidal phase on tetragonal side, and then on the rhomboidal side it's the free energy of the rhomboidal phase which is lower. This trivial result. So here in this region, the energies of the two phases must be very close. So even with the small pressures and stresses, you can transfer from one phase to another. So the polarization vector should be easily changed in that region. This is just more detailed illustration of, so this part here is what I'm showing here. So why it is transverse permittivity and shear piezoelectric coefficients which are maximized the most at morphotropic phase boundary, and what connection that has to have with the appearance of a monoclinic phase. So I will try to illustrate that, and we will start first, let's see if I can do this. Yes. So I will first show you how monoclinic phase looks like. So let's take pseudo-cubic crystal. So it can be either tetragonal or rhomboidal. Pseudo-cubic. And now for a rhomboidal phase, polarization vector is along 1, 1, 1 pseudo-cubic phase, while for a tetragonal phase, so this is rhomboidal, and for a tetragonal phase, polarization is along 0, 0, 1. So this is I'm drawing here spontaneous polarization in these two different phases, rhomboidal and tetragonal. And I'm illustrating everything on a simple cubic structure because it's easier like that. Now, monoclinic phase that has been observed experimentally in PZT at the morphotropic phase boundary, and some people think that the whole rhomboidal region is monoclinic, would actually be the phase whose polarization would be anywhere between this vector and this vector in this plane here. So that would be let's say somewhere here, somewhere here, somewhere here. Those would all be monoclinic monoclinic structures. Same type of the structure, but polarization vector can lie anywhere in that plane. And I think you start guessing where I'm heading here. When you are very close in energy between rhomboidal and tetragonal phases, then whether that vector will be along 1, 1, 1 or along 0, 0, 1, both orientations would have same energy or very close energies. Okay? And that means that with external electric fields or elastic fields, we will very easily go from here to here or anywhere in between. So that monoclinic phase comes naturally, at least intuitively you see it. If this and this have the same energy, then anything in between them should have approximately the same probability of appearing. So that this monoclinic phase appears between rhomboidal and tetragonal phases is not that unusual. Now, whether it's a stable phase or is it a phase just which exists just because of internal fields in a material that push this vector to be neither tetragonal nor rhomboidal, but somewhere in between, is for our purposes immaterial. Some people think that that monoclinic phase is there as a consequence of the boundary conditions and of the whole state of the material, and some people think that it is really a stable phase. But that doesn't matter. So so monoclinic phase you would expect, and the point that is important to remember is that that monoclinic phase is naturally related to rotation of the polarization. Okay, because to get from T to R, if you rotate the vector with an external field, you would immediately go into monoclinic phase. And since energies are here equal, that rotation through monoclinic phase has to be relatively easy. Okay. Now, this has prepared us to explain why piezoelectric coefficient, why shear piezoelectric coefficient and transverse permittivity or permittivity perpendicular to the polarization are the largest in morphotropic phase boundary systems. So I will stop here, and then we will continue this discussion because I don't want these files to become too big.